What is tissue contrast? Consider two voxels, each representing a different tissue in the blue rectangle. Signal intensity has been maximized in these tissues, and so they both appear white. Why can't we see them? The answer is that it's not sufficient to generate signal from tissues, even if we maximize that signal. We need to generate different amounts of signal from tissues in order to distinguish them from each other. These signal differences between tissues are tissue contrast. Maximizing signal from them is insufficient. We need to make sure we have different amounts of signal from different tissues. Tissue contrast before MRI often was invasive and caused harm to patients. Consider the example of pneumoencephalography. This involved performing a lumbar puncture to replace some of the patient's cerebrospinal fluid with air. Why would we do this? So let's take a look at this skull radiograph. We'll notice that the outline of the skull is fairly crisp in relation to the air that is outside of it. And that's in part related to the drastic differences in density between air and bone on radiography. We can also faintly make out the frontal sinuses. That's the right frontal sinus. Here's the left frontal sinus. We can more clearly make out the maxillary sinuses and the nasal cavity. We can even make out the inferior turbinate, which is bone, and distinguish that from the inferior meatus, which has air density within it. So this extreme difference in density between air and bone gives us sufficient tissue contrast to be able to see these structures. But you'll notice we don't see the lateral ventricles. The fluid in the lateral ventricles is not sufficiently different in density from the skull, at least on a radiograph, to be able to see them. So someone must have had the idea, well, if we can see air in these sinuses and the the nasal cavity, what if we could introduce air into the ventricles? Would we be able to see them then? So the answer is yes. So this was a patient with a brain abscess, I believe somewhere in the right side of their brain. And we can see that it's causing mass effect on the right lateral ventricle. It's effaced relative to the left lateral ventricle. There's also a midline shift. Pneumoencephalography was derived from ventriculography, which was an earlier and even more primitive method where air was directly introduced into the skull by means of burr holes. As you can imagine, these procedures were associated with significant patient morbidity, headaches, vomiting, and some patients even died from these procedures. Compared to modern cross-sectional imaging, these studies were also of limited diagnostic utility. So why am I bothering to talk about this? Why am I talking about pneumoencephalography in a lecture on MRI physics? Because I think it's important to see the lengths to which doctors are willing to go to obtain tissue contrast. It's critical to make a radiologic diagnosis. If we can't distinguish tissues from each other, we can't make a diagnosis. And MRI is exquisitely good at this. There's so many different types of tissue contrast that we can do non-invasively and safely in MRI that it's really incredible, and it's worth taking a moment, I think, to be grateful for that. So let's start with proton density contrast. So I'm not going to talk about the MR sequence parameters that are used to generate these kinds of images. That'll come at the end of this talk. But I'd like to start with looking at the differences in the number of protons associated with these different types of tissues, which will help us understand why they're either white, black, or shades of gray on a proton density contrast image. So fat and water have tons of protons, and so they're going to be relatively white on a proton density MR image. Air and cortical bone have no or relatively low amounts of hydrogen in them, and so they're going to be relatively black on a proton density MR image. Soft tissue tends to be in the shades of gray, and the way I understand that is it's primarily related to the amount of free water versus bound water in these soft tissues. So free water, like in the bladder or cerebrospinal fluid in the ventricles, that's going to be readily detectable on MRI. But water that is closely associated with macromolecules, so an example of a macromolecule in the extracellular space would be like collagen. Macromolecules that are intracellular would be actin, tubulin, or even myelin. So if there's water in close proximity to those macromolecules, these protons are considered dark. This is something I saw on Alan Elster's website. The idea is that these protons are there, but we're not going to be able to detect them on conventional MRI sequences, including proton density images. So because soft tissues are a combination of this free water and bound water, they're going to tend to have more intermediate signal compared to tissues that have purely free water, like the ventricles, for example. So let's consider this sagittal MR proton density weighted image of the knee. We'll see that fat is relatively white, which makes sense because there are tons of hydrogen nuclei in fat. The fluid is very white, and that also makes sense. Tons of hydrogen nuclei in water. The air is black, and that makes sense. There's almost no hydrogen in air as far as I know. It's just oxygen and nitrogen mostly. Cortical bone is also black, and that makes sense because there's almost no hydrogen nuclei in the calcium hydroxyapatite, which makes up the majority of the cortical bone. So question, why is the bone marrow white? So the answer is because there's fat in there, fatty marrow, and that's going to have tons of protons in it. Soft tissues like this muscle is going to be somewhere in between black and white, shades of gray. And again, that's related to the proportion of free water versus bound water that that particular soft tissue has is going to determine what shade of gray it is, essentially. So question, why is the posterior cruciate ligament black? It's supposed to be a soft tissue. Why is it not a shade of gray? So the answer is that it's mainly made up of collagen. And remember, collagen is that one of those examples of a macromolecule. And so when hydrogen nuclei, water, are associated with collagen, we're not going to see them on conventional MR imaging. That's the dark protons that I was talking about earlier. So this is one of the reasons, by the way, that I think proton density images is so useful in musculoskeletal imaging, because normal tendons are going to be black. And if you have injury to the tendon, often it's going to be white. You'll have fluid signal in there. And so this is a patient, I believe, with an anterior cruciate ligament injury, and this is a suprapatellar knee joint effusion. Okay. So before we talk about relaxation, we need to talk about excitation. Again, so to review, we put the patient in the MRI scanner, and that's going to cause the hydrogen nuclei inside the patient, mainly in water and fat, to align parallel and anti-parallel to the static magnetic field, B0, but 6 out of 10,000 are going to line up parallel to B0, and that's going to add up to the net magnetization vector. But we can't detect that yet because it's overwhelmed by B0, so we have to rotate it 90 degrees into the transverse plane, separating it from B0 so that we can then measure it. And we do that by turning on the radio frequency coil. So what I'm going to add to that is that when we're turning on this radio frequency coil and flipping M into the transverse plane, we're depositing energy into the patient, and we're putting the net magnetization vector into a higher energy state. So after we turn off that radio frequency coil, what do you think is going to happen to the net magnetization vector, given that we put it into a higher energy state? So it's just going to go back to where it came from, which was a lower energy state. So it's just going to go back to where it started, parallel to B0. So that's what happens in relaxation. But there are a couple of nuances to that. So the first nuance is that we're going to lose transverse magnetization more quickly than we're going to recover longitudinal magnetization. The second nuance is that this process of losing transverse magnetization can be thought of as taking place independently of the recovery of longitudinal magnetization. So let's dig into that a little bit more. So when I was studying this for the first time, that was really counterintuitive to me. If we're representing this relaxation process. We're going from this high energy state after we've rotated M 90 degrees back to its original low energy state where we're oriented in the longitudinal plane parallel to B0. I would think that the net magnetization vector, as we're going along this gray curve, if we're losing transverse magnetization, that means that we have to be gaining longitudinal magnetization. That's just what the graph looks like. But I want to erase that thought from your mind. There are different mechanisms which govern the loss of transverse magnetization from those which govern the recovery of longitudinal magnetization. So it's helpful to think of these processes as independent from each other. And the transverse magnetization is going to be lost much more quickly than the longitudinal magnetization is recovered. Okay, so that being said, we're ready to go into the graph. So let's first consider transverse magnetization. So before the 90-degree radiofrequency pulse, so net magnetization vector is oriented in the longitudinal plane, parallel to B0. So question, what is going to be the transverse magnetization at that point? So it's going to be 0. And then as we rotate it, so that it points perpendicular into the transverse plane, that transverse magnetization is going to go to maximum. So that's what's happening graphically during excitation. We're going from 0 transverse magnetization to 100% maximum transverse magnetization. So I'm just going to draw that 100%. Okay, so that's when the radiofrequency coil is on and we're rotating the magnetization vector into the transverse plane. So after we turn the radiofrequency coil off, what's going to happen? Well, that's what's described over here. We're just going to go back to where we started with the net magnetization vector pointed in the longitudinal plane. So it's going to go back to 0. So the question is, how is it going to do that? Well, it's going to do it relatively quickly. Remember, we lose transverse magnetization relatively quickly. So it's going to look something like this. It's an exponential decay curve. And we can describe it by a time constant. So the time that it takes to decay to 37% of the maximum transverse magnetization that we started with is T2. So T2 is the time constant which describes how quickly we lose transverse magnetization. And different tissues are going to have different T2 properties, which is going to help us to distinguish them. Okay? More on that later. Oh, excuse me, not T2, T2 star. I'll talk about the differences between T2 and T2 star when we cover the spin echo in part 2. But for now, let's just call it T2 star. So why 37%? So that is related to the mathematics of E. So if you do it on a calculator, 1 over E is basically 37%. And this natural decay process is described by the mathematics of E. So if you're wondering where that number came from, that's why. Okay, so we're ready for longitudinal magnetization, that graph. So let's do that. So we're going back to before the 90-degree radiofrequency pulse. Question, what is going to be the magnitude of longitudinal magnetization? Maximum or 0? So it's going to be maximum, right? We start off with the net magnetization vector entirely in the longitudinal plane. So the longitudinal magnetization is maximum. But then when we rotate it into the transverse plane, that longitudinal component goes to 0 because everything is now in the transverse plane. There's nothing left in the longitudinal plane. So during excitation, longitudinal magnetization goes from maximum to 0. Okay, so then during relaxation, we're going to go from this high energy state to the low energy state we started with. And the low energy state we started with, we said had 100% longitudinal magnetization. So let's just write that. That's 100%. And remember, it's going to take longer to recover that longitudinal magnetization. I'm just going to exaggerate it here. Okay, and there's a time constant which describes that. So the time constant which describes how long it takes to recover 63%, which is just 1 minus 37%. It's the same kind of math related to E. So the time that it takes to recover 63% of the maximum longitudinal magnetization that we started with, that time constant is T1. So T1 describes how quickly a tissue is going to recover its longitudinal magnetization after we turn off the radiofrequency coil. T2 star describes how long it takes a tissue to lose its transverse magnetization after we turn off the radiofrequency coil. T2 star, transverse magnetization. T1, longitudinal magnetization. T2 star is going to be much shorter than T1, and T2 star is governed by a mechanism that is independent of the mechanism of T1. If you understand that, then you're ready to proceed with me into the next part of the talk, where we talk about T2 star contrast.